Welcome to this video lecture on the Master's Program in Computing Science at the University of Groningen. I'm Michael Wilkinson, one of the associate professors involved in the course. So, the Masters of Computing Science consists of 4 tracks. There's the Intelligent Systems and Visual Computing track, there's a Software Engineering and Distributed Systems track, and a Data Science and Systems Complexity track. Apart from that, there's also a Science, Business and Policy track, which is organized faculty-wide. The admission, you require a Bachelor of Computing Science as a prerequisite, or an equivalent BSc from a Dutch or EU university. Other types of degrees and institutions, you'll need an individual evaluation. And the possible outcomes are immediate admission, tailored bridging program, like a 40 EC in size, and potentially having to do the bachelor with potential exemptions. So exemptions that we might accept also in programs in the MSc is if you have equivalent modules taken or qualifications that were acquired elsewhere, if you show convincing evidence that using certificates, course content, used literature and workloads in terms of ECTS, and the Board of Examiner accepts the request. Most of the tracks have the following outline: that you have 50 EC in terms of courses that are obligatory for your chosen track, and 15 EC in terms of the in-company placement or research internship, 10 EC guided choice courses from a list, and 15 EC free choice of courses where you can choose any master's course from any program, and you end up with a 30 EC master's thesis. The SBB track is slightly different in that there are 45 obligatory courses, 15 internship points, 20 guided choice, and a 40 EC master's thesis or internship. In all cases, it's 120 EC, 2 years of study. So, there's a number of obligatory courses or projects in all tracks. So they're common to all tracks. Web and cloud computing, 5 EC, Introduction to Data Science, and Student Colloquium. The research internship is another part that's for all tracks, and a master's thesis, which is 30 EC for most tracks except for the master's thesis and internship for SPB. The Intelligent Systems and Visual Computing track is a research-oriented variant, and it has many interdisciplinary projects, strong relationship with data science, and the main themes are machine learning, pattern recognition, image analysis, computer vision, data and information visualization. The mandatory courses, apart from the standard ones, are pattern recognition, scientific visualization, neural networks and computational intelligence, image processing, computer vision, and advanced computer graphics. And then, of course, the 30 EC of elective courses. As an example, we show some content-based image retrieval projects or shape retrieval projects, where, for instance, on the left-hand side, we have a query image of some spot on someone's skin, and the system throws up a number of candidates of similar spots and their diagnosis, so to assist doctors. We've also got projects in finding faint structures in astronomy, where there are huge data sets that need to be processed automatically. And as a result of one bachelor and master project group, we have now developed a tool which is far more sensitive. Neuroimaging. There's a neuroimaging center in the University Medical Center in Groningen, and we have strong links with them, where we map the brain. Also, if you have big data which are not necessarily sort of spatial data that you can easily make a 3D analysis from, there are all sorts of tools that are being developed to visualize these and extract meaning from a huge load of data. We also have large visualization facilities in which you can actually test your methods in a huge and rather unconventional platform. Software Engineering and Distributed Systems track is more oriented towards development of new code, also more business oriented. And software engineering is nowadays found in everything: tractors, vacuum cleaners, you name it. There's all sorts of stuff that contains including even your light bulbs, software. Now, how do we keep this software up and running? How do you make large software projects sustainable? That's at the core of software engineering. Distributed systems is also something that we all encounter. If you go to an ATM, you can withdraw cash even though your bank is somewhere in a different continent. If a single machine goes down, it shouldn't bring down the network, and that is basically a tribute to how far distributed systems have come. And the biggest distributed system of all is, of course, the internet. So there are a large number of challenges. There's an increasing integration of system engineering and software engineering. It's very much focused on how can we improve value for the users, how can we make software dependable, especially in critical applications. There's rapid accelerating change. There's complex systems of systems. You want scalability over infinite number of computers, preferably autonomous behavior of systems, pervasiveness, and of course you want these things to be efficient in terms of the energy they use. Practically any object you use nowadays, except for perhaps a football, has some software in it. So the courses that are mandatory, well, web and cloud computing, the introduction to data science are common, but software architecture, software maintenance and evolution, software patterns and scalable computing are also part of the system in the first year. In the second year, it's information systems and enterprise application integration. There's a huge number of research projects and very much in terms of connections with all sorts of companies within our country and beyond. And there's huge collaborations with industry, of course. Then data science and systems complexity. The mandatory courses are introduction to data science, information systems, scalable computing, modeling and simulation, pattern recognition, web and cloud computing, and visual analytics for big data. Data science is, of course, something extremely wide. You have complex data, you have imperfect data, you have missing values, noisy data, imbalanced data sets. Sometimes you have very few samples of, say, a rare disease and huge amount of data on the healthy cases. Underlying processes are often unknown. So how do we go from data to knowledge? That's really what data science focuses on. And how do we do that in a way which works robustly, even if the data are imperfect and noisy, etc. So we can do prediction of diseases, biomarker detection, and we want AI tools more or less that are transparent and interpretable. We want to be able to integrate expert knowledge and find patterns which lead to some sort of mechanism underlying the problem. Astronomical data science, there's a project that's going on since the summer of 2017, the Sundial project, where we study the evolution of galaxies. We want to find fainter structures, as we've been saying before. You want to find anomalies, odd things, the needle in the haystack. Systems complexity also looks at the sometimes much smaller data sets, which however have a very complex underlying mechanism, and how to model these efficiently and how to compute, for instance, the flow and the stresses around a propeller of a ship effectively is also part of simulation and data science. There are many interdisciplinary projects involved, mobile agents in, for instance, for automatic stock taking in warehouses, asthma remission, how do we reduce symptoms, why do symptoms sometimes reduce? There are often very many different data sources. Atherosclerosis, major cause of heart failure, is also an important research topic. Then the science, business and policy track. It's basically available for all science masters in Groningen, and the idea is to become a person who can advise businesses and policymakers on scientific issues. Slightly different program. It has Introduction to Science and Business, Introduction to Science and Policy, and a placement stage traject, as it's called in the Netherlands. Here we have a large number of different projects as well, together with businesses. So, for instance, subcutaneous monitoring of the electrocardiogram, but a policy project on microcontamination of drugs and water chain management. So, people take increasing numbers of medicine as they grow older, and of course, what goes in must come out, and this gets into the water supply. And how do we deal with that? What sort of policies could be put in place to reduce problems? There's a lot of innovation studies done with multinational organizations, with small and medium enterprises, with governmental organizations and non-governmental organizations. If you want more information, there's of course more to be had, then I would say go to the website, the student portal, contact the academic advisor Nicolai Klitzing, and the open office hours are shown here. So thank you very much for your attention, and I hope to welcome you at some point at our institute in Groningen. Thank you very much.